Okay, our next speaker is Scott Ketcheson. Scott is a PhD student in Wetland Hydrology Laboratory in the Department of Geography, University of Waterloo. Scott finished his master thesis within the same group on a research project of the wetland restoration hydrology, and his PhD research is now focusing on assessing the hydrological regime of constructed fen, and he will be talking about the reference constructed fen today.
That's right. Thanks for doing. Yep, so good afternoon. As you heard, my name is Scott Ketcheson. I'm a PhD student here at the University of Waterloo, and I'm conducting my research under the supervision of Jonathan Price. So today what I'd like to talk to you a little bit about are Hillslope-peatland interactions in Northern Alberta. So Sarah just provided an introduction to our big project out there, the constructed fen that we're working on Suncor's lease. Well, within the scope of that research project, we were able to go out and select a few reference sites. So the idea was that we wanted to get a range of systems that would bracket the eventual expected endpoint of that constructed fen. And so today I'll be presenting some of our work from one of these sites. So what's really interesting about the Western Boreal Plain region of Northern Alberta is, as you've already heard, there are a lot of wetlands there. So wetlands make up about half of the landscape in this area, and the majority of these wetlands, about 90% of these wetlands, are fen peatlands. So these are wetlands that are reliant upon atmospheric as well as surface and subsurface water influxes. And so because of their predominance in the landscape, they represent an important ecological and hydrological function. So the other thing that's interesting about Western Boreal Plain peatlands is that the hydrology of these systems doesn't necessarily follow surface topography. So in eastern Canada, especially in the Canadian Shield region, topography often dictates hydrology, where upland or hill slope areas provide water to lower lying areas within the landscape. Well, in the Western Boreal Plain, there's actually fairly thick glacial deposits, and some of these fen or peatland hill slope sequences have contrasting hydraulic roles. So you can have situations indeed where the hill slope feeds the low-lying wetland with water, but this role can reverse as well, where you actually have a situation where the water table elevation's higher in the wetland than it is in the adjacent hill slope, and so the wetland actually provides water to the adjacent forestland hill slope. So that's been fairly well documented over the last decade or so at a long-living research site a little bit southwest of Fort McMurray. And so they've characterized these groundwater hill-slope peatland relations. But what we wanted to do was go out there and look at the role of event-based or transient connections between the hill slopes and the peatlands. And so some of the work we were doing in the field, we started to identify periods during rainfall events and soon after where you could actually have influxes of water from the hill slope into the fen that aren't necessarily accounted for looking at traditional groundwater interactions. So in situations on hill slopes where you have sort of a porous, mossy forest floor overlying sharply contrasting hydraulic properties of mineral layers, we thought that there's potential for, during large rainfall events, for water to actually not be able to percolate down through that moss and perch up above this mineral layer, and this could potentially provide an influx of water from the hill slope into the wetland on a sort of short-lived, transient, event-based condition. So that was really what we set out to do. We wanted to start to characterize the groundwater hill slope peatland interactions in our systems, but then really identify whether or not short-lived, event-based connections were occurring, and if they were occurring, quantify how large they were, if they represented, a really substantial influx of water for these fen systems. So the site that we worked on is the Passiflora fen, we call it. It's an elongated poor fen that's situated in sort of a valley surrounded on both sides by contrasting hill slopes. This is about 40 kilometers south of Fort McMurray. And so our study focused on this sort of narrow neck region here, where we move from a slope to the west through the fen system itself and then onto a slope on the east. And as I mentioned, these are contrasting hill slopes. So in the west of the system, especially in the near fen zone, we have a very gentle topographic gradient and a fairly thick organic moss layer, so about 30 centimeters of moss overlying this mineral sediment, and it's quite gentle. And then as you move across the fen to the east slope, to contrast that, it's actually quite a steep surface topography in the near fen zone, and the layer of mossy forest floor soil layer is actually quite thin. It's maybe 10 to 15 centimeters thick, and it's overlying this mineral soil. So, as I mentioned, what we wanted to do was really start to get a sense as to how this system's functioning in terms of groundwater interactions. So we've got a few years of data now, and this is a plot looking at precipitation at the top and water table elevation above sea level in the middle of the fen, so right in between those two hill slopes. And this is across 3 seasons. And what you can see is when we put the water table elevation from the east slope onto this plot, you can see that the east slope water table is at a higher elevation than the fen for much of the season. So this means that the slope's providing water into our fen system. However, under dry conditions, we get this periodic reversal, especially in the autumn of 2013, where the water table's at a higher elevation in the fen compared to the hill slope, and the fen's actually providing water into the hill slope system. So on the west slope, we see a similar trend, although exaggerated, but we see conditions when the west slope's providing water into the fen, as well as when the fen's providing water into the slope. So to give you an idea what that looks like in terms of a cross-sectional profile, these are sort of median average water table conditions where we have a pretty gentle horizontal hydraulic gradients, and the water is moving from the slopes into the fen. This is exaggerated under wet conditions, where we have more steep horizontal hydraulic gradients and more water moving into the fen. And then under dry conditions, we see where the water table is actually at a higher elevation in the fen, and it falls off into these hill slopes. As I mentioned, we wanted to really characterize the transient event-based connections that were occurring at this site. And so to do that, we instrumented the west and the east slope in the near fen zone with these runoff stations. So these were basically gutter that we got at Rona and sheet metal that we banged into part of the slope that we had excavated just below that moss mineral interface. And so the idea was that any water that was moving along that interface would go into this gutter, and we had it pouring into a tipping bucket rain gauge. So that was being logged. And we were also measuring precipitation and interception, and we had logging soil moisture probes in profile in the moss and in the underlying mineral soils. So this is looking at data from the runoff station on the east slope. So we've got precipitation, and then this is moisture content in the moss layer and in the underlying layers of the mineral soil. And then this is the subsurface flow expressed in milliliters per hour. So this means any time that water perched up above that mineral sediment and flowed through the tipping bucket, we identified that in this plot. And what's really exciting here is that this was occurring quite often, as you can see, throughout the summer. All this data is from 2013. So it was happening a lot. And what we wanted to see was whether or not there was any sort of threshold-based response and verify whether or not this was occurring above unsaturated mineral layers. So this plot's looking at water table elevation versus the occurrence of shallow subsurface flow. And you can see that this perching of the water table occurs essentially independent of water table elevation. And so this, along with the moisture content measurements, indicates that it's happening above unsaturated mineral soils. And that's attributable to the saturated hydraulic conductivity profile with depth. So there are very sharp contrasts and differences between the hydraulic conductivity of the mosses and the hydraulic conductivity of the mineral soil. So this plot's looking at saturated hydraulic conductivity. So that's basically the ease at which water can move through a medium. And it's not on a log scale purposely to emphasize how much higher it is in the mosses compared to further deeper into the profile where you move into this mineral soil. So basically the mosses are able to conduct water much more effectively than mineral soils. So the mechanism that's happening on the east slope is that as rainfall falls on the forest floor, It percolates down through this porous moss layer, but it isn't able to infiltrate into this mineral layer, and this transient water table perches up above unsaturated sediments and provides a flux of water into the fen. So unfortunately, under the conditions that we measured, we took the volume of water that was coming in off these slopes, we spread it across the area of the fen to get a depth flux input of water from the hill slope to the fen, and it was about 1 millimeter over the summer of 2013. So this does not represent a hydrologically substantial influx of water from the hill slope to the fen. But what's important and exciting about this is it's a mechanism that hasn't been well documented. And under the right conditions, I think that there's strong potential for this to be a lot more water. Just unfortunately, we didn't have those in the summer that we measured. So now moving on to the west slope. So this is the slope that's much more gradual in terms of its surface topography. And then this is a similar set of data. We've got precipitation, and then moisture content in the moss and the mineral soils. And then again, subsurface flow, except it's much different on the west slope. You can see it only occurred twice over the whole season, but when it did occur, it was much, much bigger. So on the east slope, the same plot was expressed as milliliters per hour. Well, this is liters per hour. So this is a lot more water coming in off of the west slope into the fen, but only a couple times over the season. And that's because the mechanism on the west slope was really threshold based. So again, we're looking at a plot of water table elevation versus the occurrence of shallow subsurface flow. And you can see that once the water table rises to a critical threshold elevation, the slope really turns on and starts to provide a lot of water into the fen system. And again, that's sort of a feedback from the hydraulic conductivity profile with depth. So again, saturated hydraulic conductivity with depth. As you move from the mosses down into the mineral soils, you have a sharp decrease in hydraulic conductivity. So the mechanism that's happening on the west slope is different from the east, and that's where there's a very shallow and gentle near fen surface topography. So the water table, a slight rise in the water table allows it to actually rise up into that highly conductive moss layer. And so when the water table moves from the low hydraulic conductivity mineral sediments into this moss layer, the slope really provides much more water than it did previously. So a lot of water over a short period of time. So to put that into a seasonal flux perspective, this is looking at depth average flux from the west slope to the fen, and it's on a log scale. So you can see these two periods of time when the slope really turns on. Those correspond with when the water table is actually up into that moss layer, which is highly conductive. And so in terms of the amount of time over the season that the water table resided in the moss layer, it was very little. So about 90% or more of the season, the water table was in these mineral sediments that had a low hydraulic conductivity. It was for less than 10% of the time that the water table actually rose up into that moss layer. And in that less than 10% of the time, it was about 80% of the seasonal flux of water from the slope into the fen was received in this short period of time. So this is really interesting. It's, two very different mechanisms are occurring on these contrasting slopes that surround the same system, and they're separated only by, tens of meters, basically. And so on the east slope, where we have this steep near fen surface gradient, and we have a sharp contrast between the moss forest floor and the underlying mineral sediment, limited storage, we can have a transient perching of a water table above unsaturated mineral sediments. Unfortunately, like I said, when we measured it, it wasn't a hydrologically substantial influx of water, but the mechanism is there that under the right meteorological conditions, this could be a lot more water. And then on the west slope, it's a much different mechanism that's occurring, where it's this gentle near fen topographic slope that allows a small rise in the water table to bring the water table up into that highly conductive moss layer. And that's when the slope really turns on and provides a lot of water over a short period of time to the fen system. So both of these represent really important and potentially very important mechanisms of water delivery, of which we're very interested in a subhumid climate, especially from the perspective of designing wetlands in this dry climate. So I thank you for your time, and I welcome any questions.
Thanks, Scott. Any question for Scott? Okay, I have one question, Scott. In one of your moisture content results, you showed that the low moisture content at depths of 5 centimeter, and then there was a big difference for the 15 centimeter. Is it because of the precipitation at that time? That was sometime in October.
Yeah, was that on the east slope? Yeah, I'd say it's that very deep bottom layer of the moss that's actually becoming saturated during rain events where the water table's perching up. So I think that's why we're seeing a strong response deep in the moss profile.
Is it because of the higher hydraulic conductivity, just release or drain all the water is coming from the top layer?
Yeah, so it's really because the water can't percolate into the mineral soil, and so then it causes the bottom of the moss to wet up.
Okay, thanks again.